You have a random variable in 5 dimensions. You know it is distributed according to a multivariate normal, given a mu vector and a covariance matrix sigma. Now you want to partition this vector, which consists of an x0, an x1, an x2, an x3, and an x4, into 2 subvectors, the first one containing the first 3 entries, so let's call this an xa, which is x0, x1, and x2, and you have an xb, which contains the last 2 elements. So it contains x3 and x4. Of course, you know the probability of all the elements in joint, or the probability of vector x, which is the probability of x0, x1, x2, x3, and x4. But what is the probability of xa alone, so without the elements of xb? And what is the probability of xa given xb? For arbitrary distributions, this can be impossible to compute, but luckily we are here in the multivariate normal, for which we have analytical solutions that we want to discuss in this video on the marginal and conditional for the multivariate normal distribution. Hi and welcome to this new video. Before we start, let us look at what the partitioning means for the parameters to our multivariate normal. So here we said that we partition the vector x, which was, for this example, 5-dimensional, into 2 subvectors, xa and xb. Consequentially, this also means we split our mu vector, which consists of the mu's in each of the 5 dimensions, into 2 submus basically. So we have a mu a and a mu b. In our case, a 3-dimensional mu and a 2-dimensional mu. And then we have our covariance matrix, and the covariance matrix contains the entries, or in other words, submatrices of AA, which contains the interaction of A with A itself, so how the first 3 elements of our 5-dimensional vector interact with each other. Consequentially, we also have BB, and we have sigma AB and sigma BA, and this is our 5x5 dimensional covariance matrix. It's a metric positive definite, and based on this we can also say that sigma AB is sigma BA transposed. With this in mind, let us now start first with the marginal. And the important thing for the marginal that we have to consider here is that these interactions are no longer relevant. So the interactions, and these are sigma AB or equivalent sigma BA transpose, are no longer relevant. Why is that? That is because we would integrate out all the dependencies on the elements that are contained in the other vector. So if we want to marginalize on xa, then we would marginalize out all the dependencies on xb, and this would also of course include the interactions between the dimensions. So in this case it is straightforward to say that the probability of xa, so of our 3-dimensional vector alone, so no dependency here, is a normal distribution over xa under the parameters mu a and the sigma AA matrix, so basically the slice that is in the top left of our covariance matrix, or of our total covariance matrix. Consequentially, we also have the same result for xb, so a normal distribution over xb with a mu b and a sigma bb. And as said, there is no sigma ab or sigma ba involved anymore. This might have come a little bit out of the blue, but we can visualize it in 2 dimensions for the bivariate normal distribution. So let's look at here. So we have a 2-dimensional plot with an x0 and an x1. So here in this case, we don't have a 5-dimensional vector, just a 2-dimensional vector. But of course, visualizing in 5 dimensions is probably impossible. So let's stick with this 2-dimensional case here. And let's center our total or our joint distribution or our multivariate normal at a certain position. Let's maybe put it here. And then let's create some contour lines. So maybe something like this. And here we have our multivariate normal approximately. And we see, well, we have a mu0, so the center of the distribution, we have a mu1 corresponding to the random variables here. And let's say, for instance, the mu is at 4 and 2. Well, then let's investigate the contour lines. So we see they are no longer axis aligned, meaning that we have some covariance involved here. And I think it's also visible that the overall variance in x0, so maybe something like, or variance or standard deviation in 0, is a little bit greater than it is in the x1 direction. So here we might have a little smaller variance. And let's put this into an example covariance matrix for this case. So let's say our covariance matrix is a 2 in the 0th direction, is a 1 in the 1th direction, and a 0.5 in the covariance here. Of course, these are a little exaggerated terms, but I think you get what I mean. And the marginal we are now interested in is basically the projection of these two-dimensional contour shapes onto a one-dimensional axis. What do I mean by this? So let's take the density mass that is at a certain point in x0 and sum it up or integrate it out, and then get a certain height of our distribution basically. So this is essentially also the process that we would have if we would integrate over x1. And here we see, since we have the center of the distribution, we have a lot of mass. And then if we go a little bit more to the right, we see it's getting less, so on, and even more less, and then it gets less, and it's asymptotically converging against 0. We might get a shape something like this. And even with my terrible drawing, you probably identify this as a Gaussian distribution. Since we want to find the marginal of one component in the bivariate normal, we have a univariate normal distribution, which is just easily visualizable. And then we can go to the other random variable and do something similar, integrate over the x0 axis basically, and then we might get something like this. And of course, this is just for visualization purposes. Since we said that the variance in this dimension here is smaller than it is in this here, we also get a more narrow Gaussian distribution in this particular case. Then let's look at the terms that we figured out here. Based on this, we of course know that our mu0 will be 4. And I hope this makes sense because the univariate normal distribution is then also centered at this mu0 here. And for this, we then have mu1 at 2. So we have our univariate normal here also centered at mu1. Then let's extract the submatrices from our covariance matrix. And of course, in this case, we don't have submatrices since these are just scalar values. And we can extract the following. So we have a sigma 0 squared of 2. So a variance in 0 of 2. And we have a variance in 1, which is 1. And this then also hopefully coincides with a wider Gaussian in x0 and a more narrow Gaussian in x1. And really important, these are no longer relevant here. So the covariances are integrated out, so they're not relevant for the marginal distribution. Let's now continue with the conditional distribution. So second point is the conditional. In the marginal, we found the probability density distribution over xa alone. Here we want to find it over xa given xb. And also here we are back in the vectorial senses. So in our example, we have a 3-dimensional xa and a 2-dimensional xb. And of course, we know due to the chain rule of probabilities, this can be expressed as p of xa and xb, so the joint distribution, so the multivariate normal that we have given, divided by the marginal. Since we know the joint distribution and we just figured out the description of the marginal, you could say, well, we can also evaluate this. And that's probably not wrong, but here we are interested in a true functional description of this conditional. And for this, we will do something that is quite similar to finding posteriors in case we have conjugate priors, where we will look at the conditional. So we will ignore the normalization constant and we will just look at the joint distribution and say that the conditional is proportional to the joint, which is just a general finding based on Bayes' theorem or just by the chain rule of probabilities. And then we will figure our way towards a distribution that is over xa alone. So we will make some modifications on the joint, always using these proportional signs, and then in the end come up with a distribution over xa. And spoiler, it will again be a multivariate normal distribution. But before we start, let us note down the multivariate normal once again, which we set it to be proportional to the conditional. So this, and by equal I mean is this, it's still proportional to our conditional, is 1 over the square root of the determinant of our full covariance matrix multiplied with 2 pi raised to the power of k, and k is the dimensionality, and here in this case we are in 5 dimensions. Then we multiply this with the exponential of minus 1 over 2 of vector x minus vector mu in brackets transpose times sigma inverse times x minus mu and then closing brackets. For the further derivation, it is helpful to look at a precision matrix instead of the inverse of the covariance matrix. So we will note down that this is equivalent to using the precision matrix lambda, and the precision matrix is just the inverse of our covariance. And we can also make a subdivision of the precision matrix lambda into a lambda AA, a lambda AB, and lambda BA, and a lambda BB. And really important, since we say that the lambda matrix overall is equal to the inverse of the covariance, doesn't mean that lambda AA is equal to the inverse of sigma AA. That is really important, and we will also come back to this later. So the lambda AA is unequal to sigma AA inverse. And that is really important. So well, then let's go on plugging into the lambda, and let's also ignore the normalization constant. So let's just go for the absolute proportional here. And then we say this is proportional to the exponential of minus 1/2 of x minus mu in brackets transpose, then multiplied with the precision matrix lambda, and then times x minus mu, and then closing brackets. And now the question is, how do we come from the joint vector x to our subvector xa? So from 5-dimensional to a 3-dimensional vector. And the idea is the following, that we explicitly write down how this quadratic form or vector transpose matrix vector is evaluated when we use our subdivided vectors. So basically we will write down the exponential. Once again, equal means it is equal to this side, but it's still proportional to the conditional. And then we have a minus 1/2 here. Then let's have an opening bracket, and then let's bring in x, which is subdivided in xa and xb. You can think of it the following. You can always get to x by concatenating xa and xb. And then we subtract mu a, mu b. Hope this makes sense. Then close transpose. And then we have our subdivided matrix, lambda, with lambda AA, lambda AB, we have lambda BA, and we have lambda BB, closing brackets. And an important note, for the moment we will consider these as known, and in the end we will then find out a way in order to get the lambda AA from the other components. So not just this wrong obvious way, but the correct way. So then we multiply it with this expression again. So here we have xa, xb minus mu a, mu b, and I'm running out of space here, but I think you get the point. And in the next step, we will now evaluate all the products that appear in here. So this works as following. So I will have the exponential of minus 1/2 here again. We know that the vector matrix vector product is evaluated as following. So if we just consider this matrix vector product here in the end, we know that we get vector minus vector is a vector. So basically we would do the first row of the matrix multiplied with the difference in these two. So basically I have lambda AA multiplied by xa minus mu a in brackets. And then in order to get a scalar product, I would multiply this with this row basically. So let me note this down. We get xa minus mu a in brackets transpose. This is from this row. And then we multiply it with the lambda AA matrix multiplied with xa minus mu a plus the lambda AB matrix multiplied with xb minus mu b. And then we close the brackets for this here. recall once again. So we have the subtraction of the two vectors giving us this. Then we have the matrix vector multiplication. I see I'm missing two underscores here. And this is what we get here, which is just creating another vector. And now we made the scalar product for the first component, basically. And let's do the same for the second. So it will be this times this times this. So essentially we will be getting here an xb minus mu b in brackets transpose. Of course we have a plus here, that's because of the scalar product. And then we multiply it with lambda ba times xa minus mu a plus lambda bb times xb minus mu b. Then close and close again and close once again for the exponential. And the important step here, going from the general exponential to this, is that we now have the xa appearing in here. And recall, our big goal is to find a distribution over xa. So we now have to isolate xa in a sense. And in order to do this, we first have to multiply out all the components. This will be a little bit tedious, so bear with me. So we have the exponential of minus 1/2 and then opening brackets. So first, let us do the multiplication of this term here. We would have this subtraction transpose this matrix or this submatrix basically, and then multiply it with this one. So we will get an xa transpose lambda aa times xa. I hope this makes sense. And then since we have a quadratic form, so in essence we have the both vectors at both ends which are identical, we get minus 2 times xa transpose lambda aa mu a. And then we have the term that is in mu a purely, so we have a plus mu a lambda aa mu a, and of course it needs a transpose here. Then let's go for this term, which is the common factor multiplied with the next submatrix and this two subtractions of the vectors. So we will get a plus xa transpose, then submatrix ab times xb minus xa transpose lambda ab mu b. And here also, since we don't have a quadratic form, we have to use each of the term individually. And then we also have a minus mu a transpose lambda ab mu b. And then we have plus mu a transpose lambda ab mu b. Let me double check. Yep, this makes sense. Then we can go on to the next line where we would do this multiplication. So we have plus xb transpose, then matrix ba times xa minus xb transpose lambda ba mu a minus mu b transpose lambda ba and xa. And here you see this is somehow similar structure because we get those mixed terms basically. And then we get finally plus mu b transpose lambda ba mu a. So mu b transpose lambda ba mu a. And also take care here that the dimensionalities always match. So we have the lambda matrix ba, and we then know that it is no longer a square matrix. This one is of course a rectangular matrix. In our case, B was 2 and A was 3 dimensions, so it will be a 2 by 3 dimensions. And then it also matches the dimensionalities of XB and XA. Okay, we are almost at the finish line here. Let's do the last multiplication. And for this, we get an XB transpose lambda BB XB minus 2. And here we again have the quadratic form XB transpose lambda BB mu B plus mu b transpose, and I missed the bb here, times lambda bb mu b transpose. And then we can close for the multiplication with 1/2 and for the exponential. Okay, now we have a lot of terms. Let's try to make it a little bit clean and look at what we can throw away. So we can throw away this one here because it will be constant. And let me explain this to you. It is constant because it involves only the parameters of our normal distribution. And recall, we want to have a distribution over xa. And since we are in the exponentials, every additive constants can be put out and basically made a multiplicative constant, and then we can just take the proportional. Well, the same holds here, and it also holds for this one here. Why is that? Because we have a distribution over xa. We are conditioned on x be true, but it's not one of the main dependencies, so we can also ignore it here. Then let's go on. What do we have here? Here we can throw away this term, of course. Here we can't throw it away because we have an xa in there. This one can be ignored. And here we can throw away all of it because there is no xa involved. So then we have left, well, we have the fully quadratic term in xa. Then we have this term. We have these terms here. And we got this and this term. But we can simplify these terms further because we have a quadratic form, and we know that lambda BA is the same as lambda AB transpose. So we have the following idea that lambda BA is lambda AB transpose. And with this, we can equally write this as an XA transpose times a lambda AB times a mu B. And this is identical to this, so we can add these two up. And the same obviously is here, that we can also make this an XA transpose times a lambda AB times an XB. Okay, then we have a lot of information here. Let's try to summarize it back down. And I have to use a proportional here because we deleted a lot of components here. And this will be proportional to an exponential of -1/2 times. Then we have our quadratic term in A with the XA transpose lambda AA XA. Then we have -2 times XA transpose lambda AA mu A. And this was from the quadratic term that we had up here. This is just directly taken here. And then we can add up the 4 left terms into 2 joint terms basically and get a plus 2 XA transpose lambda AB XB and a -2 times XA transpose lambda AB mu B. And let's close it down and close it down again for the exponential. And then we are really close to finding the distribution over XA because we are left with only terms that contain XA at least. And the difference is now that this contains XA quadratically. So contains XA quadratically. And then we have these terms that contain XA linearly. And if you have terms where XA is quadratically and linearly, and you want to have one functional form over XA, this calls for a completion of the square. So that is what we will be doing in order to get our full distribution, which will be the completion of the square on XA. And what do we have to do for this? So for this, let me first rearrange it a little bit, and I will do it as following, where I will have an exponential of -1/2 and then opening brackets, and I will keep the quadratic term as is. And here I will bring out the common factor, which is always XA transpose. So we will have an XA transpose multiplied with -2 times lambda AA mu A plus 2 times lambda AB XB minus 2 times lambda AB mu B. Then close this bracket, then close the bracket for the -2 and for the exponential. And then we can identify a standard form in here that we have also done in a general video. So here we will have an A or a matrix A, and this is identical to a vector B. And also remind yourself this will be a vector because we have a matrix multiplied with a vector yielding a vector basically. Don't be confused with the naming AB. This is just to be in accordance to the video where we derived the general completion of the square. Of course, we also use a B here as to denote our subvector, so take care of this. And then we can write this equivalently as the exponential of -1/2 of XA transpose times matrix capital A times XA plus a B transpose times XA. And let me also indicate our substitution here. So we have A substituted and we have B substituted. And why did we do all this? Because we have a general result for the completion of the square if we have it in this form. And this general form is given as the exponential of -1/2 of XA minus a vector D in brackets transpose times matrix A times XA minus a vector D plus a scalar E. And then we can close this down, and we should also have the -1/2 here in the brackets. And of course, this A is the A from before. In this case, we don't have to consider the E because it will be constant in XA. So we will just take the form as is. And we can then describe D in terms of B and A. And you already see it probably that D will be the mu of the distribution over XA. Well, then what is this D vector? And in the derivation for the multivariate completion of the square, we found it as -1/2 A inverse times vector B, and I see I'm missing the double underscore here. Well, then let's plug in what we have. So we get -1/2, and for A, we said this is lambda AA, so we have to invert it, and then we multiply it with B. So what was B? B was this entire expression, so it was -2, and let's also factor out this -2 and multiply it with AA times mu A minus lambda AB times XB minus mu B in brackets. Then let's close this one and close this one. And I hope this makes sense because the lambda AB matrix is a common factor for these two summands basically. Okay, then let's multiply it out and first have -1/2 times lambda AA inverse times -2 times lambda AA times mu A. So the -1/2 and the -2 cancel, so we get a plus. And the lambda AA inverse cancels with the lambda AA, so we get a mu A. And then here we have the -1/2 cancels again with the -2, and then we get a plus lambda AA inverse times lambda AB times XB minus mu B. And just a quick discussion on this. So we say that the D, which we already identified as the mu of our conditional distribution, will be the mu A, so the mu of the marginal, plus some correction. And there is the important fact that the XB appears in here. So the XB on which our distribution is conditionalized on is apparent in where the mu of this conditional will be. So let's also call this, or as we identified it already, as the mu A given B. And then we can also identify the sigma matrix for the distribution, since we said A will be lambda AA. So we have that the sigma A given B will be A inverse basically, since we know that here is unwrittenly sigma inverse basically. So we have to invert it once again. And then we get that this will be lambda AA inverse. So we found the mu of our distribution as well as the covariance matrix basically. So we can say that P of XA given XB is the multivariate normal over XA under the parameters mu A given B and sigma A given B. And since this was probably a bit quick, let me quickly recap what we did. So we started off with the proportional on the conditional, and then we wrote down the functional form. We ignored all the normalization constants, and then we did some derivations on which we subdivided our vectors into the contributions by XA and XB, as well for the matrices. And with some completion of the square, we then arrived in a form where we could identify the covariance and the mu vector, because then we can again write down this distribution explicitly, which will then be 1 over the square root of the determinant of sigma a given b times 2 pi raised to, I will call it q, and q is the length of xa. So q is the length of xa, and in our case it was 3. So because we reduce the dimensionality basically. And then we have the exponential of minus 1/2 of xa minus mu a given b transpose times sigma a given b inverse times xa minus mu a given b, closing brackets, and this is the conditional that we found. But now you might ask yourself, wait a minute, we still only have defined our mu a given b and our sigma a given b in terms of lambda. And we don't know lambda, we only know sigma ab. And earlier we said that we can't just translate the lambda AA inverse by sigma AA. So this will be our last task. Let me phrase it as we need to express the lambda AA, the lambda AB, or actually we only need the lambda AA inverse and the lambda AB in terms of sigma AB, sigma, or let's maybe make it sigma AA, sigma AB, sigma BB, because we don't need sigma BA because it's just a transpose. How should we do this? And the solution to this is by using something that is called the Schur complement. And the Schur complement is a general result in linear algebra which allows us to define the inverse of a block-structured matrix. So for the inverse of a block-structured matrix. And what I mean by block-structured, basically this means that our matrix is composed of submatrices. And this is what we have here. The sigma matrix earlier, we subdivided it into 4 submatrices. Some of them are not even square anymore, they can be rectangular matrices. And the result reads as following. So if we have a matrix that is subdivided in an A matrix, a B matrix, a C matrix, and a D matrix, and we want to do the inverse of it, then this is equivalent to an M matrix. I will come back to this in a second. Then minus the M matrix, B matrix, D matrix inverse. So it's referring to these submatrices. And here we have minus the inverse CM. And then we have D inverse plus D inverse M, or there's a C here, and BD inverse. It's quite a tedious one, but with this we found a way in order to express this inverse in terms of these matrices and the inverse of the submatrices. And even more importantly, we only need the inverse of the D submatrix. Well, and how does this relate to our problem? For this, let us compare it with the subdivision of the covariance matrix. So we had the covariance matrix AA, covariance matrix AB, we had the covariance matrix BA, we had the covariance BB, and we wanted to do the inverse of it. This was then equal to the lambda AA, the lambda AB, the lambda BA, and the lambda BB. And with this, we can now identify what lambda AA and lambda AB is. So we can just match the patterns and see that this is this one here, and this here equals to this. So we can say that lambda AA is essentially this matrix M, I haven't disclosed yet, and lambda AB is the matrix here, minus MBD inverse, minus MBD inverse. And if we plug in the B and the D that we have here, then we get this is minus M, and B is sigma AB, and D is sigma BB, and for this we need the inverse. And now to finally answer the question, what is the M matrix? And the M is the set Schur complement. And it is defined as following, so that M is the matrix, or in brackets, the matrix A minus B times D inverse C in brackets inverted. And then let's plug in the matrices that we have. So this essentially is, well, matrix A is sigma AA, then matrix B is sigma AB, matrix D is sigma BB inverted, and matrix C is sigma BA, and then in brackets inverse. And also check the dimensionalities match. I said that the off-diagonal matrices are rectangular matrices in general, so if the indices basically have to match up, and we see sigma AB times sigma BB, so B matches with B, and B matches with B, and then we get an AA, and then we can component-wise subtract it, and we can create the inverse of the square matrix. Since we just saw that the M matrix is essentially our lambda AA, we just found an expression for lambda AA. And with the help of this, we can then go back into the parameters of our conditional distribution and find an explicit form for them. So we have a mu A given B, and recall this was defined as the mu A plus lambda AA inverse times lambda AB times xb minus mu B. And then we had that lambda AB was minus m, this expression, and then for lambda AA we had it was m. So let's plug it in. We have a mu A plus m inverse times minus m sigma AB sigma BB inverse, and then multiply it with xb minus mu B. And then we see that the m inverse cancels with the m, so here we don't have to consider the Schur complement basically. And then we are left with mu A minus sigma AB sigma BB inverse times xb minus mu B. And then we have found the expression for the mean vector of A given B only in terms of parameters that we had earlier. So there is no lambda involved anymore. And since we already know that the lambda AA inverse is our sigma AB, so in other words, this is equal to sigma A given B inverse, we just have to invert it, or essentially just remove the inverse, and then we have the inverse of the Schur complement being our conditional covariance matrix. Okay, that's a lot of derivations. Let us conclude with a summary. And for the summary, let us recall we are given an x vector. So in our case, it was 5-dimensional, and we subdivided it into a 3-dimensional and a 2-dimensional vector. We had the mean vector with its mu A and its mu B, and we had the covariance matrix given with the sigma AA, the sigma AB, the sigma BA, and the sigma BB. And then of course we knew that the probability of the entire vector was the multivariate normal over it, given the mu and the covariance matrix. And then we first found the marginal of P of XA as the normal distribution over XA with the mu A and sigma AA, and similarly for XB. And we had the conditional as P of XA given XB as the normal distribution over XA under mu A given B and sigma A given B. And we found these parameters as mu A given B as mu A plus sigma AB sigma BB inverse multiplied with xb minus mu B. And we found the sigma A given B as sigma AA plus sigma AB times sigma BB times sigma BA. And of course the sigma BB has to be inverted. And a last remark, I said this earlier, but to phrase it once again, here is our dependency on XB. So this is the dependency, or the conditional dependency. Let's put it like this. This is the conditional dependency on XB. So we of course have the parameters that are associated with B involved in our parameters, but here we also have the function value. So in other words, if you want to have the conditional on XA and you propose an XB, and let this, for instance, be only one-dimensional, and you say it's 2, then you get a different distribution than if you would propose a 4 or a 5 or a 6. And a last computational consideration, since you would need the inverse of the sigma AB anyways, it would already be reasonable to use the Schur complement as defined with the M here, because there are computational routines that allow you to get the Schur complement, and so you should already use it and not just invert it back and forth, which would be twice the work. Okay, with this I'm at the end of the video. If you enjoyed it, then please leave a like and consider subscribing to the channel. If there are any questions left, please write a comment. I would be happy to answer them. Here you will now see similar videos, and with this I hope to see you next time.